Right, so I came across these three infinite sums when I was working on an approximation for the gamma function using the Taylor series. But I thought these three infinite sums were quite nice to simplify, and they were worth sharing. So the problem with these three sums as they are put now is that for some value of a, so you would input some value of a into these, it's still quite difficult to figure out what that actual value would be. Because, well, at least at a high school level, these sums can look a bit strange. So we'll deal with the first one. So we can well, first of all, we can obviously split this series into two things, right? Of 1 over k plus a. Nothing too complicated there. But what we can see is that when this series is split into two separate series, the second series, so this one, which is being subtracted from the first, is simply the first series minus the first a terms, right? So if we just write this out, right, we can say it's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus dot dot dot. And it's minus 1 over 1 plus a plus 1 over 2 plus a plus so on. Now, we can actually see that since, as I said before, the second series is simply the first series minus the first a terms, we can actually simplify this to 1 over 1 plus 1 over 2 plus 1 over 3 plus dot 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 plus 1 over a, because all the other terms would be subtracted from this second series. And therefore, if you can see, this is simply equal to the sum from k equals 1 to a of 1 over k. Therefore, this quite unmanageable, or at least what might have looked slightly unmanageable sum at the beginning, is now really easy to calculate. Because I mean, like this, for any given value of a, you could literally just, I mean, come on, that's a lot easier to work with. So now we'll look at the second and third series, which can be simplified through pretty similar methods to each other, at least. And in order to simplify these second and third series, we're actually going to need two identities. We're going to need to know that the sum from k equals 1 to infinity of 1 over k squared, so this is basically the sum of the reciprocals of the squares, right, is equal to pi squared over 6. You might have heard of this, it's quite famous. And similarly, the sum from k equals 1 to infinity of 1 over k cubed, so all the reciprocals of the cube numbers added together, is equal to this constant called Apéry's constant, which is denoted as such, is equal to 1.20205, blah, 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 blah. It's an irrational number, but we're going to need this. So let's take the third series, right? So that third series, as a refresher, is the sum from k equals 1 to infinity of 1 over k plus a, all cubed. If we write this out, this is 1 over 1 plus a cubed plus 1 over 2 plus a cubed plus dot dot dot, right, forever. Now, we can write this out actually as 1 over 1 to the power of 3 plus 1 over 2 to the power of 3 plus 1 over 3 to the power of 3 plus dot dot dot, and then minus 1 over 1 to the 3 plus 1 over 2 to the 3 plus 1 over 3 to the 3 plus dot 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 plus 1 over a to the 3. Because it's essentially the sum of all the reciprocals minus all those terms, all those a terms before, right? Now, we can see that this first series here is simply the same as this, right? So we can say that this is equal to a priori's constant minus this 1 over 1, 3 dot plus 1 over a cubed, right? And we can actually denote this second bit here as the sum from k equals 1 to a of 1 over k to the power of 3. I hope that's pretty clear. So yeah, that kind of proves that these two are equal, and obviously this is a lot easier to work with than this, as long as you know this number. And by exactly the same logic, by exactly the same reasoning, we can basically do the same thing with the second one and say that the sum from k equals 1 to infinity of 1 over k plus a squared, which is the second series, right? We can say, right, using exactly the same reasoning, that this is equal to, instead of a priori's constant, it's pi squared over 6 because it's the square numbers, minus this sum from k equals 1 to a of 1 over k squared.